Uh, Hello, I am going to be solving exercises from Calculus Volume 1 by Tom Apostol and checking that I learned what I read. My name's Ian, and I make videos about me learning math. So, question 1 asks, what happens to the area of underneath a parabola when the parabola is defined as various functions? The first is when the parabola is defined by 2x squared. The second is 3x squared. Third, quarter by x squared. Fourth looks like 2x squared plus 1. And then finally, the general case, a by x squared plus 1. So I'll separate these out over here. I'll move that somewhere over here, I suppose, for now. And the question asks us to do two things. Like, one, draw what happens. And then two, I think like calculate the area. Like the effect on area. Okay. So in our case, this happens when 2x squared. So in a previous video, I talked about how to calculate the area underneath a parabola. So if you had a graph that looks something like this, and a parabola is a shape that looks like this, and what we wanted to calculate is like this area. In a previous video, where I talk about Archimedes' method of exhaustion, we stepped through quite a long form proof for calculating that area using an upper and a lower bound and this idea of refining approximations without actually doing integral calculus, although it's like intuitively the same. What this question is asking is to use a similar construction, but for this problem. So if you don't know what I'm talking about, go see the video over. I'll link to that video. Basically, what happened was we had like the area of a parabola. So in the standard case, we had the area of a parabola being equal to b cubed over 3, and where like the width of this is equal to b. And the way that this cube transpired was by basically just a cancellation of a bunch of terms. But if you were to look at the lower and upper bounds, you would know that you would find that the area of the lower bound is less than the area of the parabola, right? And so forth, area of the upper. And what we would find is that this can actually like arithmetically be written as b cubed over n cubed multiplied by n cubed over 3. And similarly, b cubed over n cubed multiplied by n cubed over 3 minus n squared over 2 plus n over 6. And likewise, this is b cubed over n cubed multiplied by nearly the same on the left hand as the left hand lower limit plus, except it's a positive term, n squared over 2 plus n over 6. Where these two chunks equate to the sum of n minus 1 k equals 0 of k squared, and this is the sum of n where k equals 0 of k squared. So you can see that like this sits in between like those two terms, this one and this one. Now, in our case, so to reiterate, like these series right here and here, they stem from the height dimensions of the parabola when f of x equals x squared. The k squared is that x squared, and the goal was to like construct a rectangle where the width is b over n for like n different rectangles that spanned this way, that went from here to here, here to here, etc., all the way up. And like where the x value is like some arbitrary point squared, and it turns out that like since we're drawing rectangles every b over n spaces, that the y value must be a factor like k of b over n squared, which when you pull out this term, it turns into like b squared over n squared, and you group that with this b term to calculate the area of this, which gives you b cubed over n cubed with multiplied by k squared. So the k squared term comes from all those rectangles, but basically everything stays the same. Why I'm bothered reviewing this is because we are going to have a similar construction as this, like for our as for 2x squared example, and when we are trying to figure out what the effect is, well, if we were to insert the function 2 of x squared, 2 of x squared here instead of x squared, then the result would be here. This would be 2 of x squared. This would be 2 times k bn. Oh, sorry, I guess it's on the outside. It would look something like this. And ultimately, like the final effect is that the area just increases by a factor of 2. Yep, so the geometric slices, that is rectangles, increase in area by a factor of 2, which makes sense because like what we're basically doing is like doubling up a parabola, the height of the parabola, and if the height doubles, then the area that was there doubles. And to check that that's actually true, we can actually draw it and check the intuition, but rather than drawing it, I'll just go to GeoGebra. We will plot it here where x squared is the initial parabola, and then we will if I can figure out how to use this, model 2x squared. So here's the difference. As you can see, the vertical height is doubled. Like so right here, yeah, the red curve is doubled. So I'll take a screenshot of that. Drop that here. Actually, can I? No. So draw that here, expand that a bit. And if I were to draw like a line right here and here, where this is 4 and then this is 8 and this is like x equals 2, we can see the height is doubled. Yeah, so like the argument is that like everything in here is equal, like this section here is equal to this section here, I suppose. Well, maybe not equal, but like in total, well, yeah, it is because it's a segment. So yeah, these two parts are equal. Kind of cool, but not cool enough to think about it anymore. So let's go on to the next one. Again, draw, and then effect. Our question is this: b x squared. The effect is the same. It's just changing the constant value. And if we have a rectangle and the width is b over n, and the y value is spanned by f of x, where that equals 3x squared, then letting x equal k by b over n means that f of x would equal 3 times b squared over n squared by k squared. And this part is all the same as before. So adding up the series of rectangles that create the parabola, or kind of approximate the parabola, means that we're just going to scale everything by a factor of 3. The area increases by a factor of 3. Pretty simple. We can draw it as well. So I will delete this one. 3x squared. That's what that looks like. Take a picture. Cool stuff. Next. So again, we need to draw and I'll list the effect. I will remove this. Draw it later. The effect is that the area is scaled by like 1/4. Exact same as previous examples. over 4 multiplied by x squared. And yep. So we can see here that the blue line is much smaller than the green line, and it should have a quarter of the area underneath. Next is this one. So 2x squared plus 1. What we don't know is what the plus 1 does. If we have, like I said, that series before, like this kind of construction right here. Just gonna copy this. Copy. Paste. Get rid of some of this. So again, like this came from factoring out like a long form representation of b over n by like b of f of like 1 plus f of 2 da 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 f of whatever n, and like where f of n in this case was like 1 squared, it was like 1 by b over n squared plus 2bn squared and so forth. And just by like factoring out the common like b terms, b squared over n squared from the like 1 squared plus 2 squared plus so forth, and then combining these two to b cubed over n cubed. That whole factorization activity, this is how we got here this term. We can still do that, right? When this is the f, when we let this become f of x here, we can still factorize the like 2 out of here. We can factorize the consequence of x squared, and we can also factor out the plus 1s. So let's do that. If we have a similar thing down here, we will let f of x equal 2x squared plus 1, and then we will have consequently, or something shorter, thus the lower bound would be b over n, which is the width of the rectangle, and then multiplied by 2 times like 1 by b over n squared plus 1. This is f of 1, and then plus 2 by, like this whatever. We know that it continues, da 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 da, and then 2 by n by b over n squared plus 1 over there. And this is like f of, if this was the lower bound, it'd be n minus 1, but if it was the upper bound, it's like f of n. F of n, we'll just correct this to the upper bound. So we can see that like we have these plus 1 terms get added, and because there's n of them, it'll be plus n. So we're adding like around like something like n by b over n. This gets added because it's the b over n is distributed, remember, and then the actual typical area that we have, or maybe it's better to write it this way. So we have b over n multiplied by n by like n1s, I suppose, n1s, and then plus b squared over n squared times 2 by 1 squared plus 2 squared plus n squared. Did I add enough brackets there? I think so. And so the end result is we get b over like n by n over n, so these cross out, plus b cubed over n cubed multiplied by 2, and then this this series we know approximates n cubed, n cubed over 3. So these cross out, and resultingly we get b plus 2b cubed over 3. So this scaled things by 2, and this added a constant amount to whatever b is. I don't know if we need to be more precise than that. I'm assuming not. So b and then a scaling. Cool. Let's plot this. We will plot 2x squared plus 1. It's interesting that like analytically it makes sense that the parabola no longer intersects with the x-axis because of the plus 1. It can never be less than 1 since the squares are always positive numbers. But, oh, my bad. It's unclear. Like it looks like this is the only effect, adding just like some constant value to the area. And okay. This is draw. This is the effect. And finally, A plus C, I think. So I'd say that like now we're asked again to like draw this. You can't because it's such a generic thing, but like generally if we have some parabola, it's going to go like down when c is like less than 0. It's going to go up when c is greater than 0. And then the direction as well will go up or down depending on a, if it's greater than or equal to 0, or a is like less than or equal to 0. This is like shifting. This is something like reflection. And then the effect is that scalar multiples of the quadratic term scale the area, or the trying to delete this, the amount of area proportionally whereas constant valued terms added to the polynomial or quadratic term, doesn't really matter how you put it, increase the area by the area linearly to the size of the parabola segment. Yeah, so this operates on the like quadratic term. This operates on the width. I think that's it. Okay, now we're on to question 2. Question 2 says, modify the region of a parabolic segment by assuming that the ordinate at each x is x cubed instead of x squared. Draw the new figure, and then there's like sub-questions. Here's the parabola. The ordinate's just like the height of the parabola at any given x. We know that this height is equal to f of x, where f of x is the curve of the parabola, and it's saying like let f of x equal x cubed instead of x squared, and I think it just wants us to draw the new figure. So to draw this, we are going to use a plotting software because hand computing stuff isn't worth our time. And here's that difference. I think there's like sub-questions to this question, but the things worth observing is that like there's a downward part and that x squared is greater than or equal to x cubed, at least between like when x is in 0 to 1 right here. But then x cubed is greater than x squared when x is in like 1 to infinity. Okay. The sub-questions say show the outer and inner sums, or show the upper and lower bounds using x cubed instead. So A has like show that upper bound, or I guess I'll just write it as S of n equals b4 over n4 by 1 cubed plus all of the terms to n cubed, and show that the lower bound S of n is likewise the same thing basically, but only including n minus 4 terms. Or sorry, n minus 1 terms. Cubed plus da da da. This is I think this is like really easy to prove, right? Since we know that a rectangle is b over n in width and the height is equal to f of x, and we know that f of x is like f of kb of n when we let x equal kb over n, and we know that f of x is x cubed, then this turns into kb over n cubed, which equals like b cubed over n cubed and multiplied by k cubed, and then therefore like the area of a rectangle equals b over n by b cubed over n cubed by k cubed, which this just crosses out, and then this crosses out and becomes a 4. That crosses out and becomes a 4. And then if we just like sum all of the rectangles underneath the curve, at least the positive curve, if we sum all the rectangles, this k term will come out and be the series of like 1, 2, 3, 4, etc. And that's how we will get this construction here. S of n is identical because it's just it includes one less rectangle, this one. So I think we've proven that now, which is basically right here. Part B asks us to use the inequalities, which can be proved by, okay, so it gives us two inequalities, and it says show that something holds true, like another inequality holds true for every n. I'll just write down what the inequalities are. So use these inequalities. They will be I'll just write it more concisely. The sum of n minus 1 by k equals 0 to k cubed is smaller than n4 over 4, which is smaller than the sum of n cubes. And so we want to use this one and show like s of n is smaller than b to the 4 over 4, which is smaller than s of n for every n. And prove b 4 over 4 is the only number, probably, I'm assuming only number between Sn and Sn for every n. Okay. These, just as a side note, says can be proved through induction. Again, I did a brief thing on proof by induction, although I didn't give it a great explanation, and the other YouTube video I had for methods of exhaustion and prelude to integral calculus. I don't know if we need to actually do this. It just says that we can do that. We need to show this. It's interesting that it says for every n. Oh no, there's probably actually like every n, like under the sun, n in R. It's probably like instead like n in maybe this, or maybe more likely this. Like it probably, I'm not sure if it works for negative n's or 0, and I'm not sure if it works for real numbers either. But anyway. We can show that inequality holds because this construction, or this formula right here, is not the area underneath the parabola. Again, we have the parabola and it looks something like this because it's x cubed. And if we were to construct rectangles underneath, or similarly, if we were to do a upper bound and do rectangles above, then the width of each rectangle again is b over n, which we know, I feel like I'm saying a million times, but it's b over n, and the height is f of x, right, which is x squared or x cubed. And we know, like from like the previous exercise, if we do this kind of thing, it's just going to, we can factor out like this b squared over n squared term, but in our case it's going to be a b cubed over n cubed term. but I'll write it just to be literal. So we have all these rectangles, right? We have like another one over here or something, another one over here. And rather than doing b over n by f of 1 plus, so like area equaling, or at least like the area of the lower bound equaling, I'll change it to upper bound just because it's easier to work with, plus some stuff plus b over n by f of n. Instead, we can just simplify this and factor it to b over n, multiply by f1 plus the other f terms plus f over f of n. And then I just realized I'm writing crooked, so that doesn't help. At this point, we can then start to calculate what f of the f function does, which we know is cubed, and it's like 1 cubed. Sorry, we'll do an intermediate thing and just say like let x equal kb over n. Then the cube function of 1, which is equal to k, b over n cubed, plus all this other stuff, and then cubed equals, like if we just simplify it further, the cube term is going to squeeze out, which I'm just doing to be so that it's easy to understand, but I think at this point it's not. Some people might be bored. Cube term plus n cubed by, I'll write it this way, b cubed n cubed by n cubed. And at this point we can get b over n by b cubed over n cubed by the sum of cubes, k equals 0 to k cubed, something like that, which turns into this term, which we're familiar with. So it's saying like ask to show this. We have not proven this, but what we have shown, or what we now know, is like this is the area of the upper bound, right? And we can work towards making this proof right here by then likewise showing it for the lower bound. I'm not going to do it, but it literally the exact same thing as this. And then this is n minus 1. So now we have these two terms. And we know that like this corresponds to some parabola, and the upper bound is all the rectangles that exceed it, so it has to be bigger. Like this area has to be more than the area of the parabola, and this one corresponds to a underwhelming approach where the rectangles never exceed the area of the parabola, so therefore this is always less. What we can do now is we can first create an upper and lower bound, which we just did right here and here. And then we can, with the goal of moving towards this, we can create the inequality, a inequality that uses those bounds. Like L is smaller than the a of the parabola that we have, which is x cubed, which is smaller than the upper bound. Or more literally, like b over 4. I really don't want to write this out. Maybe I'll just copy it, yeah. And this is less, and this is the area. So the next question is like, how do we move from this inequality that we have here to this right there? We can at least show that, so like, fortunately, we actually don't have to do this proof right here. It's already given to us. So we already know that the sum of cubes is, for n minus 1, is less than this constant, or sorry, this term right here, and which is also less than the sum of cubes for n. So what we can say immediately is like, this sum of cubes is like right here, right? It's like this term and it's this term. And we can say that like this has to be like, if there is, we're like, okay, well, we're almost there. We need to figure out if this term is in A. Because if it is in A, then we can argue that like the only thing that can be between, like, since they all have this term in common, then this has to, the only thing that can be in between this term and this term is the n cubed, or n to the 4 over 4. I think the way that we can argue that is we will take this inequality, or part of this inequality right here, duplicate this, bring this down here, I'll bring it down here. We will demonstrate the possible values of A. Using this, we can then take this same term and toy with it a bit, move this out over here, add n cubed here, add n cubed here. We create looser upper and lower bounds on the parabola's area, but afford us a more arithmetically arithmetically obvious description of the possible values that A can take on. For A. So using that, we get this thing. Then we have this, right? We just added the plus n term to both sides of the inequality that was right here. And at this point, we can realize that this is actually the sum of cubes all the way up to n, which is less than this term. And due to this, we can actually simplify this further because we know that S of n, or like S of n, if we multiply b over n by the sum of k cubed, which then multiply b over n on this side as well, I guess it's more like this, we will find that the left-hand side is actually the upper bound, right? This is S of n is smaller than b over n, or sorry, b over n. Sorry, b cubed over n cubed. Yeah. I think it's actually, in our case, b4 over n4. Yeah. This the b4 over n4 came from this like constant term over here, where we factored out everything, right? So like you can see that the upper and lower bounds are like, this is that same formula here, right? Anyway, so now we know that the left hand is the upper bound and the right hand will just simplify it to something a little more readable. This crosses out, plus b4 over n, right? And then it's just b4 over 4 plus b4 to the power 4 over n, which is smaller than Sn. We can do, this can be done for the like lower bound as well, and we can show that like b4 over 4 minus b4 over n is smaller than like S of n, using the exact same process, but instead of like taking this inequality, we can take where is it? We can take these two terms and add minus, I think, what is it? Yeah, just minus the term. Okay. Yeah, so sorry, what I was saying, just to make sure, like, following along, is that, like, n cubed over 4 minus n squared, and then you multiply everything by, like, b4 over 4, or n4. Sorry, I guess this is a cube. Is smaller than, like, the sum minus n cubed multiplied by b4 over 4. But this all just basically turns into like Sn. Anyway. Okay, I think this is fine to erase. Almost at the end. So now we have these two terms, like for S of n, or we have these two inequalities that better represent the upper and lower bounds. And then, as I was saying earlier, we can use these to demonstrate the possible values of A. So what we will do is say that we know that the area must be less than this because it's bigger than the upper bound. So this is bigger than the upper bound, which must be smaller than this. Here is an alternative like inequality that shows the possible values of A. Inequality. Right, and from the, or rather like knowing this, or like looking at this, the possible values of A can be like A is less than, like, so 1 is A is less than B to the 4 over 4, right? Like do like somewhere between this negative term and B 4 over 4. A can be greater, well, I'll just say this one, A can be exactly B4 over 4 or 3. A can be greater than B4 over 4, again sitting somewhere in the breadth of this positive term. We can show that and like I'll keep to this. We will show that, like, the question is asking us to do this, but we also want to do this, that A equals B4 over 4 only for all values of n. And we'll do this by doing like a contrapositive proof. We'll just show that like the other one, we will show that this case doesn't make sense. So, assume that A is greater than B to the 4 over 4. Then we can write A is less than how do we want to do this? Yeah, okay, so we'll use the existing equality, and we'll show that, I'll show in a second what I'm talking about before over n. So we'll use this existing equality, and then we will, because taking advantage of this fact that we know that, or our assumption that A is bigger than this value, it's legal to subtract B4 over 4 from both sides, which this will cancel out, like this part will cancel out, and then we will get B4 over n. And then at this point, we can simplify this further by multiplying both sides by n. This is basically an exact repetition of what I showed in the exhaustion of Archimedes, or Archimedes method of exhaustion video. for x squared, but this is for x cubed. And then this just becomes b4. And then if we divide both sides by this term, like right here, we get n is smaller than b 4 to the power 4 divided by a minus b to the 4 over 4. And like you might look at this and be like, what the heck are we doing? But remember that this value n is some arbitrary number, and it goes like as n goes to infinity, as we increase the number of rectangles that sit underneath the like parabola and like make them like smaller and smaller and smaller, because there's more of them. The left term side, like the left side of the inequality, outgrows the right side of the inequality, exceeds the constant amount because the segment width never changes, right? Constant value on the right. Hence, like what we can say is A is like A must be less than or equal to B4 over 4. Performing a similar argument as what we did by like a contrapositive proof of this, we assume that like A is less than B4 over 4. We can show the same thing. We can show that like it can't be less than B4 over 4. Performing the same argument for A being less than B4 over 4 shows that A must be greater than or equal to B4 over 4. And since we know that like it can't be greater, right, and it can't be smaller, can't be greater, can't be smaller, therefore A it can only equal B over 4 over 4 for all values of n. I guess. And that's our proof. Okay. Kind of long, but I think we answered the question now, or at least for B. There's a last thing that, there's like a question. So this answers B, but for question C, there's actually a question C. I'm just going to mark this all as being part of question B. B continued. Question C says, what number takes the place of B4 over 4 if the ordinate at each x is ax cubed? So like if f of x equals ax cubed plus c, what number replaces B4 over 4 Yeah. Okay. So it's like saying like we know that the area underneath the cubic function is a fourth of b to the 4. But if we change that function from like f of x, like the cubic function, to something that is a little more custom, like how does that change the area calculation or algorithm that we found? We know previously from like these examples that we've explored here that the a value just scales things, and then the c value adds a constant amount. So we can say that this turns into the area of the parabola equals a by b4 over 4 plus b times c. Okay, so that's that. The last question in this chapter says that there's some inequalities they give, and there's special cases of something more general. Generalize the results of exercise 2. Okay, so let's just write down the question to make sure that, because it's not very clear. So we have inequalities. (1.5) and 112. So we'll call this one A and this one B. And it says that B is the sum of cubes and minus 1 is less than n over 4 over 4, which is smaller than the sum of cubes of n. And then I will look up the other one because it's not on the actual question. Same thing for squares. Minus 1. I think 3. Which is smaller than so given these two inequalities, it says that these are general or specific cases of like this. E n minus 1 to the x to the k, which is smaller than n by k plus 1. I'm assuming over k plus 1, which is smaller than the sum of n for x to the k. And that this is like invalid for n greater than or equal to 1 in the real numbers, or sorry, the integers, as well as like k being greater than or equal to 1, also in the positive integers. It says like assume this is true and generalize the results of what we did in exercise number 2, this whole thing. So there's two takeaways, I suppose. Like one is like how this relates, how these inequalities or specific or generalized inequalities relate to the area. And then we also had a finding which was further down here, right here. So this is the general form of like what we solved, and then like I guess the question is like, how does this change with taking into account this? So let's copy this, because it seems like this is the answer pretty much. Leave some space, and we'll say the generalization of area, like of the area of the parabola, is like where this is like parameter, oops, like this is parameterized by k, which is the order or the power of the polynomial, then it's like a times b to the k plus 1 over k plus 1, and then b times c. So where k is the power of the polynomial, e.g. f of x equals this a by x to the k plus c. So we can figure out the area of this polynomial by using this function. And I think it just made us prove how to do integrals in the most general case for all. It basically just taught us how to do integrals for all polynomials, so that's pretty cool. Just by generalizing some functions. Literally, we just reused this method. Well, granted, it gave us like this thing for free, so you would have to do this inductive proof for every inequality, but generally using this and the method of exhaustion, yeah, pretty cool proof. All right, so we are at the end of the video. Thank you for joining me. I hope I didn't bore you to death, but you also learned something cool. If you have any questions, let me know in the comments. Thanks. Bye.